Okay, so I'd like to welcome you all to, I guess, our first fall seminar for the Statmos online seminar series. And today we're very lucky to have Mikyoung here from Texas A&M University. And she's going to give roughly about a 45-minute talk on Matern-based non-stationary cross-covariance models for global processes. Just before she starts, I'll just remind you how this works. So typically we're going to do the questions in the chat box, just because the audio is hard to get working for the 19 or so people here. If you have questions of clarification, feel free to ask them in the box and I'll interrupt if I see a need for that. Otherwise, we'll leave them till the end. Is that okay with everyone? Well, we'll just go with that. Okay, so enough of me. Let's all listen to Mikyoung. Thanks a lot.
Thank you, Peter, and thank you everyone to join this. I actually never given a talk in this setting, and I didn't realize this makes me more nervous than speaking in a lecture room. It's our first week, and I'm sure many of you are also having first week, and sure things are crazy, but thank you for spending your time here. So I am at Texas A&M University, and some of you may know we have pretty big group of spatial statistics people, and including me and Huyan and Matthias, and there are several other faculty who are interested in working in spatial and environmental problems. So we are very excited to join Statmos network, and I'm really looking forward to active collaboration with people. And if you'd like to visit us anytime, please email me. And I have to admit, this is my first time to do this, to join this online seminar, and it seems like a great thing to do. And from next time, I'll try to gather all of the people in our department and join as a TAMU rather than just myself. So right now, I think from our group, only my student is here. Anyway, okay, so I will start now. I'm sure some of you already heard me talking about this, but this is just based on one of my recent papers on developing parametric covariance models for multivariate processes on a sphere. So brief outline, I have objective, background, model, and application. So what do I want to do? I'd like to have a parametric function for modeling cross-covariance structure for multivariate spatial processes. So if the boldface Z is a multivariate process on some spatial domain, and if we have n many processes in the multivariate process, and for each process Zi, we decompose it into mu I and ei, and basically mu I gives the mean structure, which often is modeled through various covariates that we have. And ei is the main interest here, which is assumed to be mean zero and a multivariate normal random variable. So it's not only that each EI is a multivariate normal random variable, we want these EI processes as a joint normal random variable. So we are interested in modeling the cross-covariance structure of these EI and EJs at any pair of locations S1 and S2. And in particular, we want to have a parametric model that can deal with this covariance function. One reason that we'd like to have parametric covariance function is that if in a situation where not all the variables are observed at the same location. So if there are some locations where some of these EIs are observed, but there are also some locations that they are not observed and so on, having parametric model can be helpful to make use of all the data that we have. So I'm sure all of you are aware of the fact that even with a univariate problem, coming up with a parametric covariance function for spatial processes is not an easy thing because of the positive definiteness. And now, because we have multivariate process, for any pair of locations, the covariance is not just a one single number, but it is now a matrix, a value matrix. So we need to have a covariance function which is positive definite, and the covariance function is a matrix valued function. So recently there are many papers that are coming out in this issue, how to deal with this cross-covariance structure, and I'm just citing only a few papers that are available in the literature, especially in developing parametric classes for cross-covariance models. But we are on a sphere for this work. Most of the papers that I cited in the first slide, they don't consider the fact that the domain is a sphere. They are basically working on what we call planar domain. And in this work, we want to have a cross-covariance model on a surface of a sphere. What's the issue here? Also for this issue on a sphere, I see that now more and more people are getting interested in it. We even had a topic contributed session only focused on this issue of covariance models on a sphere. But just to tell you briefly, things on a Euclidean domain may not work on the domain of surface of a sphere. And one simple fact I'm sure many of you are aware now is that the Matern class, which is given by this form here, that I'm sure everybody's familiar. Here, alpha and beta and nu are the three parameters of the Matern class. If we simply use this Euclidean, this covariance function that we use in Euclidean domain for the surface of the sphere, and if we use the natural great circle distance on the sphere for this d, which is the distance between two locations S1 and S2, this function may not be positive definite. And there are now formal results available in the literature that using great circle distance, this Matern class is only positive definite if and only if the smoothness parameter is less than or equal to 0.5. So for a smooth process, with larger nu values, then the Matern covariance function in the usual way may not work. Usual way meaning the distance being the great circle distance on a sphere, which is natural distance on the surface of sphere. So what do we do? There are some easy things easy solution that we can use that has been also existing for a while. The easy thing we can do is instead of using great circle distance on the surface of sphere, use what's called chordal distance. And so here, basically the capital R is the radius of the sphere. And theta here is the great circle distance. In other words, it's the angular distance between the two locations on the surface of sphere. And then we all know this simple one-to-one relationship between the great circle distance theta, and here r, little r, is the chordal distance, which is the distance that goes through the sphere. People are aware that if we use r as a distance between the two locations on the surface of sphere, rather than the theta, which is the angular or great circle distance between the 2 points on the surface of sphere, then as long as we use r, any covariance function that we have in Euclidean domain, R3 or so, it should be fine. So I have been using this solution, and many other people have been using this solution in the past. And why does this work? Because simply this chordal distance, little r, that I denote here, is basically the Euclidean distance in three-dimensional Euclidean domain. So it works with no problem, even if we are thinking about the surface of the sphere. But there are some criticism for that, because obviously the chordal distance is not really a physically natural metric on the surface of sphere. So what happens when the two locations are in both poles? So one location in the North Pole and the other location in the South Pole. The colder distance is basically 2 times the radius of the Earth, which go through the Earth, which is not really physically natural distance that we can think of on the surface of the sphere. So I also see that now in the literature, there are several approaches available to deal with this issue. So basically the issue here is having a covariance model on the surface of sphere that is defined in terms of the great circle distance theta rather than r. And Joe and Monsa has a paper, and I am also working on a paper with my student, and there are other approaches using kernels and so on in that regard. But in this talk, we're not going into that direction. Another issue that I'm interested in here is what do we do when we have a non-stationarity? Again, non-stationarity is a very general and arbitrary term, and there can be all sorts of non-stationarity in the real data that we have that vary on the surface of the sphere, and there are several types of non-stationarity that I'd like to have in the covariance model that I'm developing on the surface of sphere. So what are they? If we denote Zi as the ith component in the multivariate process, and capital Lj as a latitude and little lj as longitude at a particular location on the surface of sphere. And if we consider the covariance, the cross covariance of the two processes Z1 and Z2 at two locations on the surface of the sphere, and if I denote the covariance between the 2 points as k, in general, if the covariance structure is non-stationary, the covariance function k is going to depend on the both latitude and longitude points. And then the types of non-stationarity that I'm interested in is that first of all, we want the covariance depend on the latitude, which is very commonly observed in the real data. The second one is that we also want the dependence of the covariance structure on altitude or land and the C factor, which is also natural in many applications, including climate problems. Things over the land and over the ocean are very different, and things often high up in the mountain area are very different compared to the low altitude area. So we want to have this type of dependence in the covariance model. The two other non-stationarity that we'd like to have is what people call longitudinal irreversibility, which is that the covariance between these two guys here it's not the same as covariance between these two guys, and the difference between these two is just we flipped the longitude. And another thing for the multivariate context is that we want to have asymmetry for the multivariate case, meaning that the covariance between these two guys is different from the covariance between these two guys, and the difference here is that we are flipping the locations. So what this asymmetry means is that when we look at the cross covariance matrix between process Z1 and Z2, the matrix may not be a symmetric matrix. If we have only univariate data, then the covariance matrix should be always symmetric, obviously. But for the multivariate case, the cross covariance matrix, at least for the two different processes, doesn't have to be symmetric. And we'd like to have the asymmetry in the model, which is more flexible than forcing the cross covariance matrix of two different processes to be symmetric. And basically what I propose here is taking advantage of various models that's already available in the literature. There are already several parametric models that we can apply on the surface of sphere after some adjustment, but each model have their own strength and their own weakness. And basically I'm trying is basically combining all those strengths of the existing models and have a better model. And okay, so some background on what is available in the literature. The first one is the multivariate version of a Matern covariance function that has been suggested in Knighting et al. 2010 JASA paper. This is basically a multivariate extension of the univariate Matern model. This may sound simple, but it's not simple because of the issue that we have to show that this matrix valued function is positive definite and so on. So in the end, the covariance function is given in these forms here. Here, KII is the marginal covariance function for ith process. KIJ is the cross covariance function for the ith and jth component of the component process in the multivariate process. And as you can see that both marginal covariance function and the cross covariance function are expressed in terms of the Matern covariance function. Just for those of you who are not familiar with the Matern class, this script n nu is expressed in this way here, and this script k is a modified Bessel function that is used to define a Matern covariance function. And so here nu is the Smith parameter of the Matern covariance function. A little bit about this model. This model implies that both marginal and the cross-covariance structures are isotropic, meaning that the covariance only depends on the distance between the two locations. Here, nothing is, and the spherical domain is not considered, so things are in a Euclidean domain. But using the relationship that I mentioned before between the chordal distance and the gray circle distance, we can simply use the chordal distance with this Matern model to apply to the multivariate processes on the surface of the sphere. For mathematical reasons, there are some restrictions on these parameters, nus, which is the Smith parameter. C here is the spatial range parameter, and the rho is the correlation, what they call collocated correlation, cross-correlation coefficient between the ith and jth process. I tried it, I use these models all the time, and I find it's very easy to apply, very easy to fit, and often it is very flexible. But one thing about this model is it is isotropic. So we need to do something to take care of the non-stationarity if we want to use this model. Another thing that I just want to mention about this Knighting 2010 paper is that they show how their model fits to the pressure and the temperature data. So they try to build a joint model of surface temperature and pressure. And what they show is basically their model fit is in red here. So these black dots are the empirical covariances for pressure, temperature, and their cross covariance. And then the red curve here, sort of, is their fit using their isotropic bivariate Matern model. And what kind of bothered me with this figure is this big discrepancy at the origin between the empirical cross covariance, empirical marginal covariance, and then their fitted ones. And in their paper, they say that this big discrepancy may be due to the fact that these dots, black dots, the empirical covariances are highly dependent on each other and so on. But what I found is that, so now what I'm showing here in blue and green. So green is basically a simple non-stationary version of the Matern model that's proposed here. So again, this model is isotropic, but we can make this model to be non-stationary in a very simple way, simply letting these sigma i's, which is the marginal standard deviation of the process, to vary across space. Then the fit is in green. And in that case, just simply tweaking the marginal variances so that they depend on space doesn't really work. Here, what I'm showing in blue is what I tried, and what I did is basically using letting the smoothness parameter of each process to vary across space. And I'll show you how we do it in a minute. But what I found is that actually for this particular data set, letting the smoothness vary across space is really effective in capturing this covariance near the origin. Okay. So as an extension of the multivariate Mottern model by Nightingale, there are several ideas in the literature that can be applied to make this multivariate Mottern model non-stationary. And in particular, Kleiber and Nitschke 2012, they give this, they showed that we can actually let the smoothness parameter, and here I didn't let this C depend on location, but you can also let them vary over space as well. And basically you can have a non-stationary version of multivariate Mottern model with all the parameters varying over space. And the idea comes from Stein 2005 and Pasternak and Shervish 2006 and so on. One thing to note here is that although in principle they could let the smoothness parameter and the spatial range parameter to vary over space in a certain way, in the application example in their paper, they simply let the range parameter to vary across space and fix the smoothness parameter across space. And as I said in the previous slide, what I'd like to do is actually having the smoothness parameter to vary over space, because it's just more natural for me to think of the smoothness parameter to vary across space, because smoothness parameter is more about the local property, and it's just easy for me to think of the smoothness parameter to vary across space rather than having the range parameter to vary over space. Another thing about this model is that this parameter beta here, which determines the cross-correlation coefficient between the pairs of processes, is still constant. And then Kleiber and Jensen proposes a way of post-processing the cross-correlation so that the cross-correlation also has some flexibility varying over space. But this approach does not give a full parametric form, and it's because of the reason that I mentioned earlier, in the situation where we have some locations where only a few processes are observed. So basically, if not all processes are observed in all the same locations, then we may have some problem. What's also out there, which is quite different from the model that I have been discussing, is the differential operators approach that I have been working on with Stein. And here I basically sort of describe the problems in this 2011 paper that I had, which is a multivariate version of a differential operators approach. So what is differential operators approach? So basically the idea is that we are going to apply this differential operator here. So here AIs and BIs are some deterministic function depending on latitude, which is denoted by capital L. And then we have these two differential operators with respect to latitude and longitude. So we apply this operator to a simple process Y. Here's what I mean by simple is just some simple isotropic process that we know a specific form of the covariance function. So we basically use isotropic Mottern covariance function for Y, and also we use chordal distance so that we can have things, we can make things work. So what we found in this series of papers is that this approach is quite flexible in capturing certain non-stationarities, in particular some of those non-stationarities that I described earlier. The first one is the dependence of the variance or covariance on latitude. Second one is what we call longitudinal irreversibility. So after applying these differential operators, we can show that the resulting covariance structure have those flexibilities of dependence on latitude and longitudinal irreversibilities and so on. And not only that, now by extending this idea of differential operators approach to the multivariate process. So now here for each process in the multivariate process Zi, we simply let the coefficient of these differential operators to be different for each process. So now I denote AIs and BIs. Then we can also have non-stationary cross-covariance models for multivariate process on a sphere. And for these differential operators coefficients, we simply use combination of Redoundable polynomials with certain coefficients here. So PJs are the Redoundable polynomials depending on the latitude. And then we simply estimate these Aij coefficients, which is coefficient of the coefficient Ai, and they are estimated as part of the covariance parameters, along with the covariance parameter of the Matern class 4y. So that's basically what I tried in this 2011 paper. And then I found several problems with that approach. So one sort of problem of the model that I just described now is that it is giving an unrealistic cross-correlation near the poles. So we can easily show that the correlation between these two processes, Zi and Zj, goes to 1 as the two locations go to near the poles, which is very unrealistic. This basically implies that near the poles, the two processes are perfectly correlated. Another problem that I'd like to fix for the previous approach is that we simply let these coefficients as linear combination of Redoundable polynomials. And in this case, we are actually acting as if the sphere is more like a cylinder rather than a sphere. So we are not really taking into account that the actual distance between the two locations at the same latitude level may decrease as we get closer towards the poles. So we want to fix that problem. Another issue that I didn't really consider in the 2011 model is the singularity at the poles. So here I'm also going to try various choices of these coefficients to test whether this mean square continuity of the process at the poles matter or not. So just to briefly mention, for the model that I described here, the differential operators approach model, it's actually mean square continuous at the poles, only if this limit goes to 0. The limit of this term goes to 0. If not, the model is not mean square continuous at the poles. So we want to compare the mean square continuous version of the models at the poles compared to non-mean square continuous at the poles model and see how they are different. Another issue that I'm tackling here is the non-stationarity due to the spatially dependent factor, for example, whether land and the sea matters. The model previously proposed here didn't have that in the model. Basically, this model is non-stationary in terms of latitude, but it couldn't take care of the non-stationarity depending on altitude or depending on this land and the sea factor. And so I'd like to extend the model so that we can incorporate this non-stationarity due to spatially dependent factor of, say, altitude or land and the sea factor, because it since it is very critical for climate applications. So what do we do now? The simple idea is basically, as I said, we are going to sort of extend the differential operators approach in a very simple way. And what we do is that in addition to having these coefficients coefficients to be different for each process, we are going to allow this y process who is getting these differential operators applied to also are different. And how different? We are basically going to use this non-stationary version of the multivariate Matern model in Kleiber and Nitschke for the covariance model of yi. But the focus here is that we are going to let the smoothness parameter to be different over space. So basically, this yi process is taking care of sort of the local non-stationarity, having this nu I value to be different across space, and then these differential operators are going to take care of sort of more larger scale non-stationarity depending on latitude and so on. And we can't really vary everything over space. So we are going to let the nu i's to vary over space, but we are going to fix the spatial range parameters over space. So they're constant over space. And then we can simply show that the correlation between these two guys now are not going to go to 1 as we approach to the pole, but rather it's going to go to beta ij, which was the sort of the co-located correlation coefficient term in the multivariate Matern model. Another thing we tried, as I mentioned, we are going to try various forms of these coefficients of differential operators. And in particular, we are going to see how sort of better adjusting this geometry of the sphere and also considering this mean square continuity issue near the poles matter. So instead of having just AIs and BIs as a linear combination of resoundable polynomials, here this capital P is simply denoting this expression here. So I'm going to express this finite sum of resoundable polynomials as P, capital P. And then instead of having each of the coefficients of differential operators as a finite sum of resoundable polynomials, I'm going to apply a term, and I'm going to consider these two different versions. One is that we are dividing 1 over cosine of latitude to the B term here, and then cosine of latitude term to the A here. In fact, the first form here is what we originally used in our original 2007 trigonometrics paper when we introduced this differential operators approach. But then after that, we were just not really using this 1 over cosine of latitude term. But in fact, when you think about it, this 1 over cosine of latitude is better at respecting the geometry of the sphere rather than not having this term. In the same way, instead of having 1 over cosine of latitude on B, we could have cosine of latitude on A. And they are basically simply doing the same thing, sort of adjusting the fact that the 2 points at a same latitude band gets closer and closer as we go towards the poles. But in fact, that under this second format, we can show that the model is mean square continuous at the poles for any of these coefficient values. And so, in fact, Hichenko and Stein in 2012, they actually tried this format. So we are going to see how much it matters, whether we do this one or the original one that we were doing. And what's nice here is that either you do it the first way or the second way, the number of parameters don't change. Everything is the same, except that just the parametric term of the covariance function changes a little bit because of this cosine term. I have two applications, and the reason why I wanted to have more than one application was that every data set is different, and there is no one single winning model that can fit every data set the best compared to all other models. And depending on how the nature of the data is, there are some models that can fit a certain data set better than the other. And so I basically tried two different data sets. They both are coming from the climate applications. And then I compare all sorts of existing covariance models in addition to the model that I propose and see how they compare. So the first data set is the joint modeling of surface temperature and the precipitation data. It is not a real observation, but it is climate model output. I use NCAR CCSM3 output. It's CMAP3, not CMAP5. I use a 5-month average for northern winter, which is the average from November through March. And I also average over 30 years, 1970 to 1999. So it's what they call mean state. It's a long-term average seasonal temperature and precipitation data. And the interest here is doing a joint modeling of temperature and precipitation and characterize their cross dependence. The original resolution of the model was 256 by 128, which is like almost 30,000. And I couldn't really do a full maximum likelihood estimation with it without any approximation or some computational technique being used, but I didn't really want to use any approximation or some like computational tricks because that may affect in the result of estimation and prediction. So I just simply did, randomly sampled 1,000 locations across the whole domain, and I used them to model fit. I set aside 300 locations for prediction, but here among the 300, 100 locations are common locations for both variables, and then additional 200 locations are for each variable. So in these 200 locations, not all the processes are observed. I don't know how well you can see, but this is how the data looks like. This is not actually the actual data. We did some serious mean filtering using several hundred spherical harmonics terms, which is done in my 2011 paper and other papers in the past, because we wanted basically focus on modeling the covariance structure. So we wanted to get rid of any sort of the mean structure in the data as much as we could for this example. So after doing a regression using bunch of spherical harmonics terms that depend on latitude and longitude, I think I even included altitude variable in the mean structure, then I'm working with the residuals, assuming that the mean is 0 for the residuals, and I'm showing a map of the residuals. So as you can see, most big structure that we may see are gone because of this mean filtering, but still there are some pattern, like for precipitation, we still see some high variability around the equator, and things are a little bit more variable over the land for the temperature and so on. So basically we are going to try to fit various models for these two residual fields. The second data set that I have is also a data set that I have been working on for a while. This is also coming from climate model outputs, but rather than jointly modeling two different climate variables, here I am modeling jointly the climate model errors for the same climate variable. So the climate variable that's considered here is again surface temperature, and we want to study the cross covariance of the two climate model errors. So the first model is the GFDR model, and the second model is the Hadley Center model. Don't have time to go into this issue, but we have found that there are serious dependence across these various climate model errors. And so here we are just trying to see how these covariance models capture such dependence. We do same spatial sampling to deal with this computational issue. And again, we also do same mean filtering for each climate model error. And this is the residual picture. And as you can see that for the GFDR model error, there is a clear dependence on latitude in the residual. For the Hadley Center model, it's not so much, or at least the pattern is not the same as the pattern of the GFDR model error. I try various covariance models. For the details, you have to read the paper. But just to simply go over the result, I compare basically the independent Matern model that implies no cross dependence. And I have a bivariate isotropic Matern model that Nightingale 2010 had. M2 they are versions of the non-stationary Matern model from Kleiber and Michka without differential operators approach. M4 is the purely differential operators approach that I have been working on. M3 version is basically the combination of M2 and M4, in particular, letting the smoothness parameter to vary across space, and then we also apply the differential operators model. How do models compare in terms of the likelihood fit? For the first and the second applications, I basically summarize as a table. Here, the delta AIC means the improvement in terms of AIC compared to the independent model, the Matern model with no cross dependence, and improvement meaning actually decreased amount of the AIC. And for the first example, as you see that clearly the M3 version, which is a combination of the differential operators and the non-stationary Matern model, is the winner. For the second application, however, the purely differential operators approach seems to be the winner, at least in terms of the maximum likelihood and the AIC. For the prediction, it's not that clear. It's just all over the place. So what I'm showing is I'm showing the various prediction measures, RMSE, MAE, and CRPS for various models. Here, TMP denotes temperature and precipitation. Here, L1 means the 100 locations set aside for the temperature. L2 is the 100 locations set aside for the precipitation. And P is the common 100 prediction locations for the two variables. And as you can see that there is no single winner, not only for each variable, but also for various prediction measures. They are just all over the place. There is no single covariance model that's winning for all the combinations. And you can say that the difference between these numbers are not that significant, but there are some places where the difference is a little bit more significant, like here 0.06 compared to 0.32 and so on. For the second application, similar story. So again, for the two different climate model errors, basically the winners are all over the place. And when you look at it closely, basically what I find is that for the first example, having the smoothness parameter to vary over land and the ocean is really critical. So the M3 version of the model seems to be overall the winner. For the second example, at least for describing model errors, having the smooth parameter vary across space is not that effective. It seems the main critical point is having this dependence of the cross-covariant structure across latitude. So this differential operators approach alone seems to be doing better than other models. So I think I'll stop here. And again, I tried to give all the details, but I couldn't really the time constraint. But if you are interested, you could read the papers, and I'll be happy to answer any questions.
Thank you very much, Mikyoung, for a very interesting talk. Do we have questions for Mikyoung? Oh, U Chicago is typing. Wow, some people are already trained to get going. Applause, okay.
Thank you.
Do we have any questions for Mikyoung?
Thank you.
Silent. There's some typing going on. Okay, so U Chicago, do you see any need for longitudinal irreversibility when you're looking at long-term averages?
Okay, so I didn't actually. Okay, so I have looked at this issue a little bit, and longitudinal irreversibility. When we see like how the fitted model, so when we go back to the Okay, so here, like for the longitudinal irreversibility, so we compare these two covariances, and obviously for both empirical values and the fitted values, the difference of this covariance is not going to be zero. But the number that is not zero, how significant is it? Not quite sure how significant it is. Often it doesn't look that significant. But what I would say is that so this one character this characteristic, I mean the property of this differential operators model, it has various things, but it has this in particular it has this longitudinal reversibility and also asymmetry in the multivariate sense. If it's not that useful or if it's not necessary, I thought at least even just having a term model with varying marginal variance, just by letting the variance depend on latitude would be enough. And when I compare the two, sort of the differential operators model compared to the term model with only the marginal variance depending on latitude, at least the differential model, differential operators approach seems to be doing a lot better. So in that sense, I think having it is helpful, but I guess it's a choice. Like, is that really significantly helpful? Yeah, that I'm not sure, especially for this long-term average.
Okay, we have another question. Murley asks, what are the overall recommendations if we have to analyze multivariate global spatial processes and the focus is entirely on prediction?
That, I mean, it's not just an issue of the process on a sphere, but I guess it's just issue of any spatial process, because it's true that my frustration is that I see these models, more flexible models, are clearly winner in terms of likelihood or AIC, but in terms of prediction, it's not the case most of the times. So in that sense, what is the best model to fit in terms of prediction? If we I don't think there is a simple answer to that. But for like really for practice, if we want to analyze this multivariate global spatial data um, well enough, then I think even this isotropic multivariate Mater model or just a simple non-stationary extension of this multivariate Mater model often seems to be doing pretty well. But what I would say that for that non-stationary extension of multivariate Mater model, I would ask people to consider letting the smoothness parameter to vary over space rather than the spatial range parameter to vary over space. In Brazil, there was a big discussion about which one to vary and is it really feasible to vary feasible for the smoothness parameter to vary over space. But at least my limited experience is that having the smoothness parameter to vary over space for climate applications and so on is quite effective.
Great. Any other questions? Silence. So I've got one small question here, and you mentioned about mean filtering. For being able to fit these models to the residuals, so to speak, does it require quite a bit of filtering to get out large-scale features, or not so much?
Right. So I think I kind of misspoke when I was discussing this application. So for the first data set, we actually did pretty serious filtering. We had almost 300 spherical harmonics terms to get rid of the big features that we see. For the second data set, which is it's a climate model error. And what do I mean by error? It's basically the difference between the observation and the climate model outputs. There, you don't need that much because most of the big features are taken care of by the observations. The model errors are taken care of by the observations. But still, when you look at simply the difference between the observation and the climate model output, there are some features that are left, which is in particular depending on altitude and so on. So you need to do a little bit of filtering to take care of that, but not so much compared to the first application.
Right. Okay. Any other questions? Okay, well, I'm going to do a clap on behalf of everyone, but as you can see in the chat window, everyone gave you lots of applause as well. So thank you very much for taking the time. Let me just finish up today by giving a little advert for the next seminar. So hot off the presses, if I get the right file. No, wrong one. Try again. That's the problem if you give the same file name to, there we go. So we haven't got a date and time yet, but in October, our seminar will be given by Michael Schurer. And this is a request, actually, that people have wanted to talk a bit more or understand a bit more about proper scoring and assessing predictive performance and issues like that. And so we're going to have a talk about that in October. So we'll leave it there for today. Thanks again to Mikyoung, and
Thank you.
You'll hear through the email channels when we come up with a time and date for